Rightio, g'day students. Welcome to our lesson today on the synthesis of fuels. So today we want to look at a range of fuels. We're going to look particularly at biodiesel today. We'll look a little bit at ethanol as well. So the point of today is that you should be able to understand that fuels, including biodiesel in particular, ethanol and hydrogen, can be synthesized from a range of chemical reactions, including addition, oxidation and esterification. We should also describe using equations the production of ethanol from fermentation and the hydration of ethane. And then we'll also describe using equations the transesterification of triglycerides to produce biodiesel. You can see that there's certainly been a steady increase in fossil fuel production. So that's what oil and coal and natural gas. And so what are they? They are huge carbon sinks in the crust of the earth that we dig up and we convert to fuels to power our lifestyles. I should talk to you about the 1970s. So back in the 1970s, there was a group of nations called OPEC. Now the oil producing nations, and they banded together to just limit the supply and drive up price. You can see this here, and that made them a little bit richer, but it certainly got a lot of other countries that were consuming oil quite scared, and so they would develop oil production in their own nation. So rather than importing it from the Arab countries, for example, or Venezuela is another big oil producing nation. Coal, you can see, is also that's just fossilized swamps, whereas what oil is fossilized dinosaurs and stuff like that. Natural gas will sit on top of oil, and that's all three sources of fossil fuel have been growing steadily in terms of their production. So energy production is increasing, and we've got these limited resources, haven't we? Because once it's gone, we're going to have to wait for a long time for it to form again. So there's a real concern between the fossil fuels running out and also the link between fossil fuels and climate change. So there's going to be this increased interest in identifying new and sustainable forms of energy, and we're particularly thinking about biodiesel today. Talk briefly about ethanol and hydrogen will be another day to discuss. If we have a look up the top left-hand corner, you can see that we've got a fairly typical biodiesel molecule. So biodiesel is our first one we're going to look at. What's interesting here, it's longer. So it's a longer chain than a normal petrodiesel one. So we've got a few extra carbons in the chain. We've also got something going on here too. So we'll talk about that in a moment. And if it's plant-based, we're going to get these double bonds changing the shape of the biodiesel molecule as well. So first of all, if we think about transesterification, that's when fats and oils are mixed with short chain alcohols to produce methyl or ethyl esters and glycerol. So we can call biodiesel these fatty acid methyl esters. That's a mouthful. And we'll also get glycerol as a byproduct. Now the reaction conditions for this is a low temperature and pressure. Use a base as a catalyst, so sodium hydroxide for example, and to deprotonate the alcohol. So remember, hydrogen is the proton there, so we're just getting rid of the hydrogen out of the alcohol. Now you can use fats and oils from agriculture, so tallow from animals or crops such as soybean, canola, corn and sunflower to produce oils for biodiesel, and those will have to have similar combustion properties to petroleum diesel fuel. Remember, if we're thinking petroleum diesel fuel, I'm thinking about the fossil fuel there as opposed to the biodiesel. So plant-based biodiesel contains these double bonds where we had a look at here, and what's that going to do? It's going to change the shape of the molecule. It's going to put a little kink in it, and that's going to make it harder for those hydrocarbons to pack together, and that means that the dispersion forces between the molecules is going to be less, and so that's going to lower the melting points. Now, what do we think? Animal fats won't have that particular kink, so that might be more like an animal fat compared to a plant fat-based biodiesel there. Now, the reaction between to produce a biodiesel is we've got a triglyceride here, so that's palm oil, for example, so palmitic acid, mixing this one with a methanol. And you can see that we just need this catalyst as described there. So we've got the base, and we're going to produce glycerol and then this fatty acid methyl ester, which is our biodiesel. When you compare both petrodiesel and biodiesel, they have a higher energy content than petrol. So they're going to be used for larger machinery, for long haulage, for example. So it's just you get more energy per litre of fuel, and that's going to be higher than petrol. Now, they both produce similar emissions, but remember that biodiesels, especially plant-based biodiesel, it's a renewable resource, so you get it from plants. So it's already part of the carbon cycle rather than digging it up out of the ground and adding it into the atmosphere. We can note that what plants photosynthesize, and they're going to take up the carbon dioxide from the atmosphere. So biodiesel's got to be more sustainable and have a less impact on global emissions because it's using plants. Now, spilt biodiesel is also biodegradable, so it's going to be less toxic to the environment. And it'll have less particulate emissions, so less particles coming through the exhaust. If we think about the viscosity of biodiesel, it's thicker. It's got these longer molecules, so it's going to have higher intermolecular forces, so those dispersion forces. So in colder climates, it's going to build up in the fuel lines and filters, so you're going to have to put in additives, or you might have to blend it with petroleum-based diesel. And biodiesel is also more hygroscopic, which just means it's going to absorb water, and that's because of that oxygen in biodiesel is going to help create a dipole. So remember, we just got a partial charge there, and that means it's going to be able to absorb water. Now, the presence of water in your fuel is not necessarily a good thing. It's going to make it harder to combust. So you just need to think of means to keep the water out of the fuel there. So just to remember, biodiesel is part of the carbon cycle. So rather than just digging it up out of the ground, which is a huge carbon store, and putting it into the atmosphere, the plants where it comes from, of course, will absorb the CO2 emissions from the carbon dioxide from burning the biodiesel. Now, if we have a look at petrodiesel versus biodiesel in terms of sourcing, so crude oil, you can get it at land or sea. It's going to be non-renewable. Once it runs out, it runs out. Digging out crude oil or drilling for crude oil often will be located in environmentally sensitive locations. And spills are going to damage the local economy. And remember, oil is flammable, so it will cause a lot of pain to the ocean where it's burning on, for example. Whereas biodiesel, it does require intensive farming, so it will damage the environment, particularly if it's a monoculture. But crops are renewable. The crops will require water and fertilizer, and the soil will deteriorate if you're growing the same crop year after year. So there are some environmental impacts of biodiesel, which are quite negative. Now, the farm machinery will also produce carbon dioxide and other pollutants, and high quality farmland will be used for growing fuels instead of food. So if we think about the world's hunger problem, that's going to be an issue, isn't it? So do we use our soil and our farmlands for food or for growing fuel? So that also means that come a year where you need to feed animals or something, your source might not be there for industry. You might have to send the canola crop off to feeding cattle, for example. Now, when we're thinking about production, oil refineries will produce significant emissions due to all that excess hydrocarbons being burnt off with fractional distillation, and you're going to need energy required to operate the refinery. But biodiesels are going to produce a lot less emissions, but they will still need some energy to operate the biodiesel plant. Now, there are quite a different number of ways to develop a biofuel, and I've spoken briefly just about biodiesel. We'll talk briefly about bioethanol in a second, but your textbook's got an interesting example about algae, and you can see that there's first, second, third, and fourth generation thoughts out there. So algae is a really interesting area of research at the moment. Now, if we think about ethanol, so you'll be familiar with the E10 fuel, and ethanol will burn as part of the fuel, and we can produce ethanol two different ways. We can do it with a substitution reaction involving a haloethane, so it could be like a chloroethane, for example, but this is slow, so industry tends to use an addition reaction between ethene and steam. So ethene gas is steam's passed over the ethene, I believe, and that's going to be like a silicon catalyst, which is a silicon structure. It's coated in phosphoric acid, which is H3PO4, and that's going to be the catalyst there. Now you can see we've got the catalyst there, phosphoric acid, 300 degrees. So that's got to mean that that's steam. And you can see that it's 60 to 70 atmospheres, so 60 to 70 times the normal atmosphere that we breathe. Now, ethene comes from crude oil, and it takes a fair amount of energy to create the steam, even though that reaction is slightly exothermic. So you'll get about a 5% production of ethanol with each pass of ethene over the steam, but with multiple passes you get up to about 95% efficiency. It takes a lot less energy, though, to ferment carbohydrates. So, and those carbohydrates, we're thinking particularly glucose, which is C6H12O6, and just use some enzymes to turn that into ethanol there, and a bit of carbon dioxide. Okay, we've done a little bit today, and read through those learning goals. Make sure that you understand that biodiesel and ethanol can be synthesized from a range of chemical reactions. And what we looked at? Addition and esterification in particular. We looked at the equation for the production of ethanol and noted that we can do it from fermentation or the hydration of ethene. And we also looked at the trans-esterification of triglycerides to produce biodiesel. Once you're on top of that, please work on the mastery questions today.